In this module, you will learn about the principle of mathematical induction. You have seen the proofs for theorems, statements, and corollaries in your previous classes. We proved the Pythagoras theorem by using definitions and facts. The square root of 2 is an irrational number. This can be proved by contradiction. However, this method cannot always be used to prove all mathematical statements. Let's look at a simple example. Riya is the daughter of Chetan. Rohan is the brother of Riya. Chetan is the father of Rohan. In these sets of statements, the truth of the last statement can be established only if the first two statements are true. This means that the truth of the last statement is established by deductive reasoning or logic. Let's apply deductive reasoning to the following mathematical statements. 3 has 2 factors. A prime number has only 2 factors. 3 is a prime number. A mathematical statement is a statement that has a definite truth value. That is, true or false. Among the statements given, the first 2 statements are true. This implies that the third statement is also true. Thus, here we can conclude that deductive reasoning involves logical steps to arrive upon a particular case from a general case. However, inductive reasoning is the counterpart of deductive reasoning. This is commonly used in mathematics, where collecting and analyzing data is the norm. This is a process of establishing general principles from particular cases. In mathematics, we come across many mathematical statements, formulae, and theorems that cannot be proved directly. To prove such kind of statements, we use the principle of mathematical induction. To prove mathematical statements through the induction method, we must follow certain principles. The basic principle behind mathematical induction is that if a statement is true, then the statement that follows the first statement is also true, and so on. Consider a mathematical statement P of n involving natural number n, such that the statement is true for n equal to 1. Or in other words, P of 1 is true. If the statement is true for n equal to k, where k is a positive integer, then the statement is true for n equal to k plus 1. In other words, if P of k is true, then P of k plus 1 is also true. This is also referred as the inductive step. Assuming the statement is true for n equal to k in the inductive step is called inductive hypothesis. Then, P of n is true for all natural numbers. Principle 1 is a statement of fact, while Principle 2 is a condition. If P of n is true for all n greater than or equal to 2, then the first step starts from n equal to 2, and we verify the result of P of 2. Next, if the second principle is true for n equal to k, then it is also true for n equal to k plus 1. Let's look at an example. The formula for the sum of the first n odd positive integers is n squared. Let this statement be P of n. This can be proved by replacing n with 1, 2, 3, and so on. Let's first consider n equal to 1. That is, 1 is equal to the square of the first odd positive integer. Thus, P of 1 is true. This statement can be considered as a fact. Now, we will take n equal to 2. The sum of the first two odd positive integers, 1 plus 3, is equal to 4, which is equal to the square of the number of terms, that is 2. Thus, it is proved that P of n is true for n equal to 2. Next, consider n equal to 3. That is, first, 3 odd positive integers, 1, 3 and 5. The sum of the integers is 9, which is equal to the square of number of terms. Thus, P of n is true for n equal to 3. Now, let's consider if P of k is true, where k is a positive integer. We need to prove that P of k plus 1 is also true. Since P of k is true, we get this statement. Let this be equation 1. Let's add 2 times k plus 1 minus 1, the next odd integer, to both sides of equation 1. On simplification, the right side of the equation becomes k plus 1 whole squared. This is equal to P of k plus 1. Therefore, P of k plus 1 is also true whenever P of k is true. Hence, P of n is true for all natural numbers n.